Alrighty, we are going to start with a couple of warm-up problems. We're still talking about domain from functions, but we're going to see a little bit different type of functions today. So I want to start with warm-up problems where we determine what values for x would make these functions undefined. Remember, undefined means that essentially in this case, since we're looking at fractions, it means we've got something over 0. So it could be as simple as just a number over 0. It could be maybe a quadratic over 0, but the idea is values for x that would make the bottom 0. That would make our function undefined. So if we take a look at our first example here, x plus 5, we're looking at what could I possibly plug in for x here that would make the whole bottom be 0. In some cases, it's a little bit easier if you actually just set the bottom, the denominator of your fraction equal to 0 and solve. We would get, if we solved for x here, -5. X cannot be -5. If I plug in -5, -5 plus 5 is 0, and my function would be undefined. For my second example here, again, might be a little easier if I actually set it equal to 0 and solve. This would be, let's move the 10x over. So I have -2x equals -10. Divide both sides by -2, and we get x to be 5. So x cannot be 5. If I were to plug in 5 here, I would have 10 minus 2 times 5. 2 times 5 is 10. So that would be 10 minus 10, which is 0. The third example that I have here, definitely one that I would go ahead and set equal to 0 and solve. For the first one, you could probably reason through to get -5 here and 5 on that one, but I would probably need to solve on the third one. So same idea, I want to get the x term by itself. Divide by 4, and I would get -7 over 4 here. So x cannot be -7 over 4. And again, this one, maybe I want to write out my steps to check, where the first couple, probably a little bit easier to do in my head. Here, if I multiplied, I would be able to reduce the 4s, and I would have -7 plus 7, which is 0. That would make my function undefined. For my next example, same idea. If you solve, you would subtract 9 and divide by 3. You might also, though, be able to look at this one and say, hey, x cannot be -3, because if x is -3, I would have 3 times -3, which is -9, plus 9 is 0, and our function would be undefined, or our expression, I should say. For my next example, again, a couple ways that we can think about this. Some of you might be looking at this and saying, well, x cannot be 2, because 2 squared is 4, and 4 minus 4 is 0, and you are absolutely correct. I just want to point out, though, that this is one value that would make the bottom equal to 0. We have another. X could also not be -2, since -2 squared would also be +4. And then similar idea here, but for this guy, again, I might want to set equal to 0 and solve. So I'm going to move my 36 to the other side. We have 4x squared equals 36. Divide both sides by 4, and I get x squared equals 9. From here, if you can tell me that x cannot be 3 and x cannot be -3, awesome. If you want to go ahead and take that square root to find that x would be positive or -3, so then x could not be positive or -3, that works too. What we're going to see today as we're working are problems like this where maybe I set equal to 0 and solve, but we'll also see problems where our old buddy factoring is going to come back into play. So with that last example, I want to review a little bit on some of the sort of processes of factoring. So a lot of what we're going to see today will be either something called a difference of squares, which we'll get to a little bit later, or a trinomial, something with 3 terms, like what we're seeing here. So for the example that I have here, this time we're kind of work backwards, because I don't have my whole expression. I have parts of it, and then we're kind of missing that guy at the end. So what we want to do for something like this is take a look at what we do know. I want my function to be undefined when x is 4. If I think back to some of my earlier examples, like this guy, for example. We were undefined when x was -5 because I had x plus 5. If I'm undefined when x is 4, that must mean I have x minus 4. So if I were to factor the bottom here, one of those factors would be x minus 4, and the other factor would be, I'm not sure. I know when I multiply -4 by whatever that other factor is, I'll get that b that I'm trying to find. The other thing that I can look at is my coefficient for my x term. That would be -1. So -4 plus whatever that factor is should be -1. The only thing I could fill in here would be 3. That means my other factor has to be 3, x plus 3, which means that b then would have to be -12. Just a little review, some of the things that we look at when we're factoring before we move in to our really big topic for today. So with our warm-up problems out of the way, I want to talk about our big ideas for today. So we're still talking about domain. This time we're going to talk about the domain of something called rational functions. So rational functions are defined officially as the ratio of two polynomial functions. If you remember, a polynomial is something like y equals x, or y equals maybe x squared minus 3x plus 4, or x cubed minus, or we'll do plus 4x minus 2, something like that. I've got, the idea is I've got a variable as my base, and my exponents are all integers, positive integers. So if we look at our rational expressions, ratio means I'm essentially making a fraction out of those polynomials. So polynomial on top, polynomial on bottom. That's a rational function. When we're deciding the domain of a rational function, we're going to have values that we need to exclude from the domain, because if I plug that value in for x, it would make the function undefined. So that was what we were looking at with our warm-up. What values, if I use them for x, make my function undefined. So same idea here, looking for the same thing. The only part that we're adding in now for our examples is that we'll state the domain of the function. So if we look at a, I cannot plug in 2 for x. That means that I need to exclude x equals 2. Because if I plug in 2 for x, I get 0 on the bottom and my function is undefined. I don't want that. My domain cannot include x values that make my function undefined. So my domain would be all real numbers except for 2. So here's how I would write that. I'm going to use interval notation for today. So -infinity up to 2. Since I cannot include 2, we'll do a parenthesis. So this would be everything smaller than 2. If I thought about this on a number line way back to the beginning, this would tell me, hey, anything smaller than 2 is fair game. But that's not the only thing that I can include in my domain. I can also include stuff that's bigger than 2. So I want my little union symbol here. And then, hey, anything that's greater than 2 is also fair game. So 2 to positive infinity. Again, parentheses, because I cannot include 2, and infinity is not a point that I can actually have in the domain. It's this idea that we continue forever. But this would be my domain. So we had one value to exclude for A. For B, we're going to take a look and see what values do we need to exclude here. So I've got factored form already. So we're looking at what would make each factor equal to 0. So we need to exclude x equals -3. If I use -3 for x, this factor would become 0. And then it doesn't matter what this one is, because 0 times anything is 0, and we're undefined. Same idea over here, except for our second factor, we would exclude x equals 1. Our domain then will have to break up into pieces based on these excluded values. So I have to stop my domain anytime I hit an excluded value. Just make sure you're putting them in order. So I would have -infinity up to -3, and then I've got to stop and break, because I can't include -3. But I can do bigger than -3 up to +1. But I can't include 1, so we stop and break, and then anything bigger than 1. So 1 to infinity. For C, same idea. Again, we're already factored here. I'm going to pick out my values to exclude. This one's easier to see. I would exclude x equals -4. For this guy where I've got that value in front of x, if you need to set that equal to 0 to figure out that value of x like we did for our warm-up, that is perfectly fine. So we would get 4/3 that we also need to exclude. So my domain, again, would be all real numbers except for these guys. So as I'm writing my domain, I'm going to break anywhere that I hit these values. So -infinity to -4. Again, make sure you're hitting them in order. And then -4 up to 4/3. And then 4/3 to infinity. For D, I have x squared on the bottom. That means I need to exclude x equals 0. So my domain only has to break at 0 this time. So -infinity to 0, and then 0 to infinity. For E, I have a problem similar to one we saw in our warm-up with x squared -4, but this time I'm going to go ahead and factor. This is what we've called a difference of squares. So I'm going to factor this off to the side up here. Difference of squares because it's a difference, it's a subtraction of two perfect squares, x squared -36. X squared gets me x squared, and then 6 squared gets me 36. Difference of squares we talked about in Algebra 1 because it has this sort of like special pattern or shortcut that we get to use. Once I've identified what I squared to get the first thing and the second thing, when I go to write my factors, the first thing goes at the front. The first thing that I squared goes at the front. The second thing, or the thing at the back, goes at the back, and opposite signs in between. So x plus 6 times x minus 6. So I'm going to write my factored form for this because it's going to make it a little bit easier for me to see what my excluded values are when I've got these linear factors rather than something squared. So I can see here that I want to exclude x equals -6 and x equals +6. So my domain then will be -infinity up to -6. Again, parentheses because I cannot include -6 in the domain. That's what we just saw here. And then -6 to +6. Every value in between those two excluded values is fair to include. And then anything greater than 6. So 6 to infinity. For our last example here, we're going to factor again, but I want you to remember that we always start factoring by first looking for a GCF. And we actually do have a GCF, a greatest common factor here. I could divide both of these terms by 2. That's what GCF means, greatest common factor. What can I divide all of these terms by? I could divide all of these terms by 2. Since my lead coefficient is negative, I'm actually going to divide out -2 or factor out -2. That would leave me with positive x squared, and then 50 divided by -2 would be -25. So I can see, again, I have a difference of squares here. What did I square to get the first thing? What did I square to get the second thing? That's going to help me get my factored form. So to get 25, we would square 5. And this sounds like a trick question, but to get x squared, what would I square? I would square x. So my factored form here with my -2 in front would be x plus 5 times x minus 5. So I can see now that I have my linear factors that I would exclude -5 and +5. So my domain would be -infinity to -5, and then -5 to +5, and then +5 to infinity, anything bigger than +5. When I'm looking for the domain of a rational function, I do not have a one-size-fits-all option. For polynomials and exponential functions, we were able to say the domain is always all real numbers. For square root functions, for log functions, we had to look at those functions specifically. I had to make sure the step under the square root, the radicand, was greater than or equal to 0. For a log, I had to make sure that the argument was greater than 0. So I had to look at those on a case-by-case basis. The same is true for rational functions. I'm going to have to describe the domain on a case-by-case basis. But what we can say in general is that when I'm deciding the domain of a rational function, we must consider what values of x make the function undefined. That's what we were doing here. What makes this undefined? Undefined. And exclude those values. Exclude them from the domain. So that's the big idea. What values of x would make my function undefined? Exclude them from the domain. Let's look at a few more examples together. So I'm on page 21 now, and we've got a practice that includes all different types of functions here. We're going to go through a few together. I'm starting with a rational function, so I'm going to look for what functions or what values of x, what values of x would make this function undefined, and we'll exclude them. So we're going to exclude 2 and 3. So my domain then would be negative infinity to 2, 2 to 3, and 3 to infinity. My next function, g of x, is a square root function, and I know that the radicand, the step under the root, must be greater than or equal to 0. It's okay if it's 0, because we can take the square root of 0, but it can't be negative, so it's got to be at minimum 0. So I'm going to solve for x here. Remember, when I solve inequalities, it's the same as solving equations unless I'm multiplying or dividing by a negative number. Otherwise, I treat it exactly like an equal sign. And here, this would be a perfectly acceptable way to define my domain here. X is greater than or equal to negative 7. If you like your inequality domain to be in 3 pieces with x in the middle, it would look like this. If you like interval notation, it would be 7 to infinity with a bracket at 7, because we can include 7 in the domain. H of x is a polynomial function. The functions we've had where I've had to make some special considerations were things like rational functions, where I was dividing by something that had an x, square root functions, or logs. This guy, no square roots, we're not dividing by anything, it's not a log, so our domain here for this polynomial is all real numbers, negative infinity to infinity. For a log, remember that the argument, the stuff we're taking the log of, needs to be greater than 0. Okay? I can't have 0 as the argument. I can't have a negative number as the argument. It's got to be greater than 0. So from here, I'm going to solve for what values of x would keep that greater than 0. Remember, the only time that I do anything different is if I multiply or divide by a negative number. I'm dividing by a positive number, so I don't need to change that sign. So my domain here would be x values greater than negative 4. If you like the 3-piece inequality with x in the middle, it would look like this. If you like interval notation, it would be negative 4 to infinity, right? Greater than negative 4, but a parenthesis because we're just greater than negative 4 this time. There are a few problems left here on page 21. I'm going to leave those for you for homework. And then I want to take a look at the next page, just some factoring review problems together. We did a lot of work factoring in Algebra 1. I want to do a little refresher of some of those things together today. So when I've got 3 terms here, we call that a trinomial. For today, we are only looking at trinomials whose lead coefficient, whose a value is 1. So we can look for factors of c that add to b. So what would multiply to give me 24, but add to give me negative 11? If you are stuck, make a list of factors for that number. Start with 1 and go in order. So 1 times 24, 2 times 12, 3 times 8, 4 times 6. 5 doesn't go into 24. 6 does, but it's already in the list. So I've made my whole list. So these are all the positive factors of 24. Remember, I could also multiply a negative by a negative and get a positive 24. So I see that I want numbers that add to negative 11. 3 and 8 would add to 11. If I make them both negative, they would still multiply to positive 24, but now they would add to negative 11. So my factored form would be x minus 3 times x minus 8. Same idea for my next problem, my next trinomial, factors of 20 that add to 12. If you need to make a list, make a list. You may already be thinking, I think it's 2 and 10, and you would be correct. Multiply to 20, but 2 plus 10 gives me 12. So my factored form is x plus 2 times x plus 10. My next problem here, my last one in this row, is a binomial. It only has 2 terms. Remember, we said a minute ago that my first step is always to look for a GCF. I did not have a GCF for this first or second problem. There was nothing I could divide all of those terms by. In my second problem, 12 and 20 do have a common factor of 4, but my lead term here does not. So I can't divide 4 out of everything because it's not a common factor for every term in the expression. My third problem here, though, does have a GCF. I could divide both of these terms by 5x. 5 and 30 are both divisible by 5, and they both have an x. So when I divide out 5x, I would be left with x. And then 30x divided by 5x, that would be 6. So 5x times x minus 6. At this point, I don't have any more x squareds, so I am done. We're down to what we call linear factors. I'm going to go through just a couple more with you here. Back to a trinomial, back to something with 3 terms. There's no GCF, there's no common factor for all of these terms. So I want something that multiplies to negative 18, but adds to negative 3. To get negative 18, I would need 1 positive and 1 negative value. So just something to keep in mind as I make my factor list. 1 times 18, 2 times 9, 3 times 6. 4 doesn't go into 18, neither does 5. 6 does, but it's already in the list, so I've got everything. If I want to multiply to negative 18, one of these will have to be negative. In order to get negative 3, I would need positive 3 and negative 6. So my factored form would be x plus 3 times x minus 6. For my next example, I want 2 numbers that multiply to negative 45, but add to 4. If you need to write out your list, write out your list. But we're going to want negative 5 times positive 9. So that would be x minus 5 times x plus 9. I need one positive and 1 negative so that I can multiply to a negative number. I want the 9 to be positive so that I get positive 4. And then our last one in the row here, negative 12. I would want factors of negative 12 that add to positive 1. That would be positive 4 times negative 3. So x plus 4 times x minus 3. And we'll do one more together here. The start of the next row, again, I've got 2 terms here. We do have a GCF in this problem. Both of my numbers, both of my coefficients there are divisible by 3. And both my terms have an x. So when I divide out 3x, in my first term, 3x squared divided by 3x would leave me with x. And then 6x divided by 3x would leave me with 2. So 3x times x plus 2. For homework, you're going to finish the rest of the problems on page 21, where you are telling me the domain. And then the rest of our factoring examples here I will leave for you.